address CASPA this afternoon. And thank you. And I chose as the title and theme for the talk, "The Soft Overcomes the Hard." And just to get in the spirit of the Chinese aspect of the Chinese-American connection, that's kind of a philosophy from Tai Chi or the Tao Te Ching, something like that. The idea that the soft, in many ways, can be more powerful than the hard. And so let's see if that's true in robotics as well. So first, many of you, from just chatting before, do know who SRI International is.
Yeah, of course.
Sorry?
Yeah.
But perhaps there are some people in the room who don't. So SRI is a not-for-profit corporation, and it was originally Stanford Research Institute, part of Stanford, and it became independent in the 1970s, and it absorbed Sarnoff Research Corporation, part of RCA, where they've done a lot of semiconductor work. And you have probably recently used at least one of SRI's inventions. And so you see some of the more familiar inventions, the computer mouse and the Siri interface for the iPhone. And perhaps, since I'm speaking about robotics, you may not be aware that that there is also a history with Intuitive Surgical, the US's largest robotic company. And we have done other pioneering work in robotics, in particular, Shaky, the first mobile autonomous robot. And we're headquartered right here in Menlo Park. So who am I? Well, I am not a semiconductor professional, I'm a mechanical engineer. But of course, these days, there's no isolating yourself from the world of semiconductors. And I studied robotic control systems. And really, my entire career has been in a robotics lab, with a small exception, as you see in the lower right-hand corner, where I left for 2.5 years to save the world, and I did water and sanitation in Ecuador. But why have I been in a robotics lab for 25 years? Well, it's a lot of fun, and I'm surrounded by a lot of smart people. And one of my big accomplishments in that lab that you'll hear about upcoming in the talk is the development of artificial muscle, which is one embodiment of the soft overcoming the hard. It's can we make robots behave more like natural creatures with soft materials than very rigid creatures. And so I've kept that philosophy, and being a mechanical engineer, I kind of use mechanical engineering to force materials and systems to do what I want. And if I speak faster, we'll touch upon, in the end, another way to look at being soft, in terms of soft being good, and how robots can be a force of good in the world. So where are we now in robotics? Well, for the most part, not including the tires, robots are made out of hard materials, very hard structures, hard motors, hard everything. And even if you consider an exoskeleton to be a robot, by the way, is there a pointer on this? That's okay. Even if you consider an exoskeleton to be a hard robot, there's still something a soft body slips into, but an exoskeleton is still a very hard structure. But nature is not comprised of hard structures. And without that, nature can still do many things that traditional robots can't do. From high dexterity activities such as knitting, such as jumping very, very high like a flea, such as flying and changing wings, such as running very fast due to the elasticity in the tendons, being able to curl around an object like an elephant trunk, or even being able to fit into something through a passageway no bigger than your eye, like the octopus. So many possible reasons to go soft with robots. But maybe it's not just the capabilities, maybe it's just the fact that it's cheaper. So we don't need to be limited by what nature can do, but we can be inspired by it. So I'm going to talk about how these improvements are affecting robotics in many different areas. I'm going to highlight some of the innovations of SRI and end up with some of the materials work that I've personally been closely involved with. So we've heard a little bit about wearables so far, and it's okay to have a hard wearable in your pocket, but if you're really going to be fully integrated with the wearable, you might think you want to wear the Iron Man suit, but you'll really be in a cage all day. So you really don't want to be like Iron Man. You really want to be more like Spider-Man. And in human augmentation, it can be for military activities, it could be for many sports, and it could also be for therapy or for helping people who have various physical disabilities. So we have developed a platform technology that we call Superflex, which enables physical augmentation of individuals. It has different aspects to it. I want to focus on the Flex Drive and the Flex Grip. The Flex Drive is a very lightweight, low-profile muscle. So it's almost like you can strap muscle on top of your own muscles to make your own muscles more powerful. And the Flex Grip is the soft and comfortable way of attaching that to the body. Muscles are attached directly to our bones, but I don't think we want to drill into our skeletons to make attachments, so we need a nice way of attaching to the body in a way that's comfortable. And of course, we need a nice controls interface as well, and I'll talk briefly about that. So as I mentioned, the Flex Drive uses a very powerful yet low-cost motor, and it spins very fast, and it uses a very simple way, just twisting together two cables to enable a high-speed motor make something be able to elongate, contract like a muscle. So very simple idea, but very powerful implementation capability. And the Flex Grip is a unique way. I'm not sure what they call it in China, but in the US, they call something a Chinese finger cuff or Chinese finger trap. And it's something you can put on your finger, and if you pull on it, the more you pull on it, the more it squeezes. And so it has various other names, and that's the principle we use to be able to very uniformly squeeze the limbs. And so that's why we're able, this is not an employee receiving punishment. This is an employee testing out the Flex Grip, and he's able to hang with all his body weight from this because it's very evenly squeezing the limb and distributing the load. Oops, I'm too fast. There we go. And so we have developed this. We put the muscles to augment the human calf. And so when you're walking, carrying a load, actually it's the calf muscles that do much of the work on level ground. So we focused on augmenting the calf muscles. And we did testing that showed that you can actually use less energy to walk with a heavy load. And here's an example. We were funded by DARPA, an arm of the US military, to help make systems for soldiers. So you can see a very lightweight, comfortable system, and yet it helps them walk and potentially carry heavy loads on level ground. The boots were normal boots. It's strapped from the calf to the heel. Ooh, that was strange. Let's try that video. Had some strange thing that didn't show up on my computer. Oh well, everyone turn your head to the side and you can see a walking robot. So that is a robot that uses motors and gears. But so most people think of walking robots still as walking like this. Whereas people are very fluid and they use elasticity. And so this has springs built into it so that it walks in a much more fluid, natural gait. And so it was actually able to be 20 times more energy efficient than other robots. I said DRC. DRC is the Darpa Robotics Challenge. That was a recent robot competition where robots had to simulate rescue in a building, such as in the Fukushima nuclear disaster. So they can use 20 times less energy to carry for the robot to walk. Very, very important. And here's another way of thinking about robotics becoming soft. Also for DARPA, the US military, we're making micro robots that work together in a factory. So it's kind of like 3D printing, but imagine you can now carry small objects in addition to liquid, so much more powerful than 3D printing. There you see the small robots. Another reason why, and it can change surfaces, it can crawl all over everything. This is another reason why I call it soft. The robot can move on soft and flexible structures. That's a flex PC. And we can have hundreds, even thousands of them all moving together in unison. And so perhaps we can do many things that you can't do with 3D printing. As I mentioned, these robots are working together to glue together small pieces of carbon fiber, and it is building together a carbon fiber truss. So it's making structures that are extremely strong and extremely light. This is just another version of it. You can see it's grabbing one element of the truss and gluing it into place using ultraviolet light to cure it once it's in place. There you see the robot moving on different surfaces, carrying the materials around. And for simplicity, we only have one or two robots moving at a time, but there, like I said, there could be thousands, and you could be creating these truss-like structures very fast. So there you see, after some period of time, it has built a very strong truss-like structure. And I also want to comment that one of the goals with this, since you can both print materials like plastics and metals, which many 3D printers can do, but you can also move solids, so you could carry bare chips or any combination of chips and surface mount components. So you could literally do something like print a smartphone. Very, very powerful. That's about as close to semiconductor processing that I'll get to in the talk today. Now I want to focus on what I briefly alluded to, smart structures and smart actuators. So a lot of people have been starting to look at that for robots, using air pressure to make robots that are all soft and can do very interesting things. Air pressure is very good, but many times you don't want to carry around a compressor with you, and it's also noisy. So can you do something that's all electric? Well, we've been looking at electroactive polymers. Now, there are many types of electroactive polymers, and the kind that was invented at SRI we call dielectric elastomers. And I'll explain why it's called dielectric elastomers. So it's basically an insulating polymer or a dielectric that's soft pliable. And on each side of it, we apply a conductive material, an electrode, that can also stretch. And now when you apply a voltage across this dielectric material, the electrostatic forces cause it to squeeze in thickness and expand in area. And you can do a lot of things with that. For some reason, the videos are not playing as they do on my computer. So, sorry, this doesn't really work properly. Yeah, I'll just be able to click. So you can see, oops.
Move the mouse there.
Yes, I'll do it. No, that's not a light. Well, I get my
Like a
computer.
PDF, not a PDF cannot do it. Not a PowerPoint. So you cannot point to something else.
Sorry? Yeah. I will keep going while. Just, sorry for the technical difficulties. Thank you for your patience. So one thing in the semiconductor industry that you can please do is make memories that turn on instantly. I think the world is growing very tired of waiting for computers to reboot. All right, so, okay. There you get to see the walking straight up. So very natural walking gait. And we'll skip that. Okay. And now you see the muscle squeezing in thickness, expanding in area. And now here you get a sense of why we call it an artificial muscle. It behaves a lot like natural muscle. And so, since it behaves a lot like natural muscle, you have to do things like create biceps to prove that it's a muscle. Or perhaps you can move fingers. This was on a robot hand that was designed to play a trumpet. But you can also take inspiration beyond people. You can take inspiration from lowly creatures like cockroaches, which have remarkable, if you ever tried to chase one and kill one, you know that they're very hard to get a hold of, so they can move very quickly. And so we want to grab their principles and make robots that are inspired to move like as well as cockroaches, using compliant actuators like the artificial muscle. You can also make muscles that not just elongate but bend, and you can connect them in parallel or series. If you connect them in parallel, you have something that walks like an elephant but is nothing more than actuators connected to a platform. If you connect them in series, end to end, you get something like a snake. And if something is very compliant, perhaps you can control surface texture. We already mentioned the octopus. We know the octopus can deform quite a bit, but the octopus is also a master of camouflage. And not only can it change its color, but it can change its texture. So we can make programmable surface textures using highly deformable polymers. So you can feel the interface with your smartphone. You can make programmable braille or more. But where are we now with the artificial muscle? Well, you can't buy a robot that has the artificial muscle. For now, we're doing small things in haptics and with various optics. So, but there are a few companies out there, including Artificial Muscle Incorporated, that have successfully commercialized this technology for things such as gaming consoles that have very realistic feel, and speakers that enable you to actually feel sound, not just hear it. And also the technology works backwards as sensors. We've heard a lot about wearables. We can make rubbery, stretchable sensors that can be woven into clothing. Unlike many other sensors, these artificial muscles, you can see a very straight line. They're very linear and they're very low hysteresis. So a lot of good potential capabilities in using these materials as sensors. And you can actually buy these off the shelf now. In gripping, it is very hard and expensive to make robots that have sophisticated hands that can grip a wide variety of objects. And so people are making very soft, compliant grippers that mold around the object. And that's good. You can grip some impressive things very cheaply and very simply, but you're still ultimately limited by friction. We have taken our lessons learned from applying voltage to deformable materials to now creating electrostatic forces on surfaces to do what we call electroadhesion. Make materials just like rubbing a balloon on your head and sticking it to a wall. It uses electrostatic forces to get two surfaces to stick together. And we have even hung 75-pound weights on surfaces doing that. And we created a spin-off company right here in Santa Clara that is looking at materials handling using this principle. So you see in the movie, with something made out of almost no structure at all, it can grip and handle a very wide range of objects, from an apple to a can and anything in between. We can also put it on conveyor belts, as you see there, or make very large grippers that can grip very thin uniform materials, such as very thin glass for displays. or even fabrics for clothing assembly. It's revolutionizing clothing assembly in Asia, even as we speak. Well, they might be sleeping, but pretty soon they're going to revolutionize clothing assembly. But you can also make robots that can stick to walls. So this graphic, I don't want to take time now, shows that there are many ways to stick to walls: suction cups, chemicals. But electrostatic may not be the strongest, but it can grip almost any type of wall, from something fairly rough like concrete to very smooth like glass. And so here you see an example of one of our wall climbing robots. In the left-hand side is driving up the wall of our building, which is made out of very rough concrete. So you can imagine robots that could do construction inspection, or drive up to your windows and spy on you, until the previous speakers figure out how to prevent that. And another interesting thing is, you can even climb on very dirty walls. There you see we're putting talcum powder deliberately on the wall, and that's not going to stop it. Even putting the talcum powder right on the robot. And it can still drive up a cement wall. So now we've talked about the benefits of soft, but what if, but of course sometimes you want to be rigid. What if you had a material that can sometimes be soft and sometimes be rigid? What if you could go from rubber to rigid? Well, there are many things you might want to do. You might want to be able to make aircraft that can change shape. You might want to make automobiles that can change shape. Many of you may have seen BMW's concept car that can change shape, but that's just covered with some flexible fabric. Not really good aerodynamics. You can also make lots of things that can change shape. You can absorb vibrations. And in the upper right-hand corner is a sea cucumber, which again, reaching out to China, I believe, is consumed widely in Asia, not so much here in the US. But it has a very unique principle, and that's when it is frightened by a prey, it goes from something very soft and compliant and quite tasty to something that is very rigid. So that's another example of going from soft to hard. And in the interest of time, I'll skip this. So how do we do it? Again, we become very adept at using electrostatic forces. So in this case, if we use electrostatic forces to change the connection between materials, we can change a pathway from going through a rubbery material to going through a rigid material. So voltage off, it stretches like rubber. Voltage on, it's as strong as the most rigid material. And here's an example of it. It's going to, in the rigid state, so it's in the compliant state. In the rigid state, it's going to hold a 50-pound weight, and then it's going to go compliant again. So soft, like rubber. Now it's rigid, it holds to 50-pound weight, and then we turn it off, and it's soft like rubber again. And we can make that into a different form. We can make a bendable material that's soft and flexible when it's off, and then it becomes rigid when you apply the voltage. And so what do you want to do with these materials? Well, you can do things like make robot hands that now have the capability of the sophisticated, expensive hands, but are as cheap as the soft, compliant ones. If we put this rigidizing material in each joint of your finger, we can determine whether that joint bends or not. And why do you want to do that? Well, now you can use just one motor, one heavy, expensive motor to bend the finger, and we can decide where we want the finger to bend, at joint 1, joint 2, or joint 3. And this is just showing that the capability to do this is made on conventional complex PC technology. So it's very low cost, very simple because it's just electrostatic. Showing such capabilities. This is showing a soft sensor embedded as well. And the other reason why you might want to do it is you can lift something that's stronger than your own grip, stronger than a motor, by locking the joints. And you can combine pneumatics and these locking materials to make some robots with capabilities like an elephant trunk or snakes that are really made out of all soft materials. So here we're just going to have something that inflates and elongates, but then we're going to make one side of it hard. See? So it's off, we inflate it, it elongates, but now we're going to lock one side of it, and we're going to elongate it again. So what's going to happen when one side can't elongate? It's going to bend. So with just one air pump, we can make this robot do many sophisticated motions. And it's very light, very soft. It's no more complicated than a balloon. We can also make prosthetic sockets or interfaces to the body that change from soft to rigid on demand. When a person with a prosthesis needs to run, you need a very rigid interface to keep it tight. But if that same person were sitting here today listening to the presentations all afternoon, they would not want a very tight, rigid connection. And with this material, it can automatically know whether you're moving, and when you're sitting down, it can relax, and now you have something that's very compliant. When I play the movie, you see one of our artificial muscle sensors. When you see the blue, it is in a soft state, it's stretching. And when the person presses the button, you don't see the blue because now it becomes a rigid structure. So material is changing from soft to rigid at the press of a button or automatic. And we are using these, just like you saw the motors, assisting people. It turns out if you can control spring forces just by harvesting the energy from one part of the motion and releasing it later, you get increased human performance. So we have done these kind of tests as well and shown that capability. So I've talked a bit about how soft robotics can revolutionize robots. And of course, someday we would like to get to the T1000 shape-shifting robot. We're not quite there. We're working on it. Some people have even shown the ability to control liquid metal, but I think there are a lot of, I don't think we have to worry just yet. So I would like to conclude. There's another way of thinking about hard and soft. We can think of hard as being cold and impersonal, and a lot of people are very afraid of robots. They think robots are spies. They think robots are killer drones. They think robots are going to steal your jobs. And they are all those things. But there can also be, I hope you saw some examples of how they can really help us. And we think robots can be a powerful force of good in the world, whether it's taking away very dangerous or boring jobs, or whether it's helping children. You see the logo for Solid Suit. That suit that you saw that was originally designed to help soldiers is now being applied to young children who have muscular dystrophy, so they can maintain their body strength for longer periods of time and lead more normal lives. So that's why we believe in the philosophy of good robot. So, thank you for giving me the privilege of speaking this afternoon, and of course what I've talked about is really the product of many individuals' work that I can only take a small amount of credit for. Thank you.
Thank you very much, Roy. Is there any questions for Roy?